So far we've talked about two different ways of getting energy out of white dwarfs. The first is if you have your white dwarf and an accretion disk around it. As gas works its way in through the accretion disk closer and closer, it gives up gravitational potential energy, and that leads to dwarf novae. The second way is you get a white dwarf and you pile a layer of hydrogen on the surface, and eventually that layer of hydrogen becomes so thick that it undergoes nuclear fusion and blows off, and that gives you a classical nova, 100 times brighter than dwarf novae. But now we've come up with a third possibility, the idea that you make the white dwarf so massive that it starts to shrink. And as it shrinks and gets smaller and smaller, eventually the density and pressure becomes so large that it can actually fuse carbon and oxygen into iron. As we just talked about in nuclear physics, iron is the most stable element. It's got the perfect balance. And so this will liberate energy. And the question is, how does the energy you get from this compare to the two things we've talked about over here? So let's work that out. The way we can work it out is look at the mass of carbon, oxygen, which is what you're starting off with, and iron. Now for carbon, the mass is typically 12.0107 atomic mass units. An atomic mass unit is 1.67 by 10 to the minus 27 kilograms. Oxygen has very similar atomic mass, so it's 15.9994. So there are 12 nucleons, 6 protons and 6 neutrons here, whereas there are 16 nucleons, 8 protons and 8 neutrons there. So this gives a mass per proton or neutron, which is per nucleon, of 1.00089 U per nucleon. And here it's 0.99996 U per nucleon, so very similar. But if you look for iron, it's got a mass of 55.845 U, which comes out as 0.9972 U per nucleon. Now that may not sound like a very big difference, but it's telling you that about 0.3% of a difference in mass. If you take carbon and oxygen, and you get the right number of nucleons from them and combine them, so 56 to make iron, you'd think it would weigh 56 times as much as a single nucleon, but it actually weighs a little bit less than that. And that little bit less is caused by the binding energy. This little bit less, the fact that that number is a little bit lower than those numbers, is because the nucleons are stuck together with such strong binding energy. And energy equals mass, according to Einstein, according to the famous equation E equals mc squared. So, if we take one nucleon in the form of, say, carbon, and convert it into iron, so that same nucleon ends up in iron, we can look at how big the mass difference is. So let's just take carbon to iron. We could take oxygen to iron and get very similar answers. The change in the mass is 0.00366 atomic mass units, and that's just the difference between this and that. So every time you take one nucleon of carbon and somehow combine it so it's part of a nucleon inside iron, it weighs a little bit less. And that tells us that energy must be released. The energy is given by E equals mc squared, so the energy is equal to the mass, which is 0.00366 times the definition of an atomic mass unit from up here, 1.67 by 10 to the minus 27. So that gives you the mass multiplied by the speed of light squared, so 3 by 10 to the 8 meters per second squared. And that comes out as 5.5 by 10 to the minus 13 joules per nucleon. So every time you take a nucleon, a proton, and a neutron, and which is sitting inside a carbon nucleus, and do some nuclear physics to get it inside an iron nucleus, you get this much energy out. Doesn't sound like a lot, but Of course, there are a lot of nucleons in a white dwarf. So how many nucleons do you have in a white dwarf? Well, what we can work out is the energy not per nucleon, but per kilogram. So energy per kilogram equals 5.5 by 10 to the minus 13 divided by the mass of a nucleon. Because 1 over the mass of the nucleon is how many nucleons you have in a kilogram. So the mass of a nucleon is the same atomic mass unit, roughly speaking, 1.67 times 10 to the minus 27. You can worry about whether it's this times the mass of the nucleon or that, but that's going to make very little difference here. Which comes out as about 3.3 by 10 to the 14 joules per kilogram, which is a lot. A small atomic bomb is maybe 10 to the 11 or 10 to the 12 joules, so this is a fairly medium-sized atomic bomb, as you'd imagine, because atomic bombs work from the same principle, nuclear fission or fusion. So that's how many we get per kilograms. How many kilograms in a white dwarf? Well, to make a white dwarf shrink down enough to fuse things, it's going to have about 1.5 solar masses. So that's 1.5 times mass of the sun, which is 2 by 10 to the 30 kilograms. Multiply this by that, and you end up with an energy yield of about 10 to the 45 joules. Whoa, that's a big number. That's a very big number. It is much bigger than classical novae, let alone dwarf novae, which are 100 times even wimpier. So, if you could get this to happen, if you could get a white dwarf to shrink down and fuse carbon and oxygen all the way through the middle to form iron, you're talking about some sort of explosion that's much, much bigger than the explosions we've been talking about so far, which by themselves are pretty violent. We're talking about not really some nova, but something much worse.